Okay, welcome back. So last time we talked about simple hypotheses and constructing tests in critical regions to test our null versus alternative hypotheses. For example, we discussed using the Newman-Pearson lemma to construct a most powerful critical region of a given size alpha. But now, what to do in the case of composite hypotheses? Now, we could consider fairly general composite hypotheses. So, hypothesis, right, is just some assertion concerning the distribution of the population that we're considering. Concerning the distribution for a population. Typically, it has to do with the value of some parameter. Or maybe some collection of parameters. Okay. Now, there are certain special cases to consider that typically come up more frequently. So let's just say often it might be something of the form this parameter has a certain value, or maybe this parameter is greater or equal to some value, or maybe it's less than some value, or maybe that it's not equal to some value. These are typical kinds of tests that we might look at. A common occurrence is that where the null hypothesis is simple, but the alternative hypothesis is composite. So simple null hypothesis. H0. So in other words, it specifies, for example, like some specific parameter which then completely defines our distribution, let's just say, and a composite alternative, H1. If we construct a test of this sort to distinguish between a simple null hypothesis and a composite alternate, we often call these a test of significance. So such a test, I haven't specified what the test is. I'm saying, you'll then give some criteria based on your experiment, based on some value of some statistic that comes out of your samples, and then you'll decide whether to accept or reject the null hypothesis. Such a test that you then design is called a test of significance. And the alpha is called the significance level. Remember, alpha is the probability of a type 1 error. More specifically, this composite alternative often has one of the following forms. So common, subcase or whatever, subcases are that the alternative hypothesis is of the form, let's say theta is greater than the value that the null hypothesis specifies, or maybe theta is less than the value that the null hypothesis specifies, or maybe simply that it's just not equal to the value specified by the null hypothesis. These things would be called one-sided alternatives, whereas these would be called two-sided alternatives. Okay, and these hypotheses would be one-sided or two-sided alternatives, and the tests would then be called a one-tailed test or a two-tailed test, depending on which of these things you're looking at. So the corresponding test would be one-tailed or two-tailed tests. So a lot of the examples are going to be of this form, and these come up rather frequently. So the important thing to that I want to discuss then is, how does one come up with with such a test, like a test of significance or a more general test of maybe comparing to a composite hypothesis. So unlike before, where we could discuss what's the probability of a type 1 or type 2 error, there won't be a single probability, but rather it'll depend on this parameter which is not completely specified by the hypothesis itself. So let's just give an example to kind of get the flavor of what we're talking about here. So again, we'll look at a coin flip, aka a Bernoulli trial, Bernoulli random variable. And let's say theta is the probability of a heads, of the coin coming up heads, or probability of success, or however you want to call it. And we'll have these two hypotheses, H naught, that the coin is fair, so in other words, that theta is equal to 1/2, and we'll look, for example, at the one-sided alternative, that the parameter is, let's say, bigger than 1/2. Okay. Now, let's also look at an example of a test. So our test in this case is going to be accept the null hypothesis unless 4 heads. Now, I should say, actually, there's a bit of difference of language and, I suppose, of meaning, really, that one often ascribes to these tests of significance, which is to say that because there is such a lack of ability to quantify your type 2 error, that one typically doesn't say, often doesn't say that you accept the null hypothesis, but rather that you reserve judgment. The null hypothesis is it's not like we're declaring that the coin must be fair if the test doesn't come up 4 heads. I mean, that seems like a very strong assertion to make, although, it's a coin, it's probably fair. But whatever, like if some random Bernoulli variable or whatever. Just because it doesn't come up 4 heads, that doesn't mean that we have a lot of evidence that the probability is 1/2. It rather just means that we cannot, based on the evidence that we've observed, discount the null hypothesis. So we're going to reserve judgment. So I've written accept the null hypothesis. I've often said it in terms of accepting the null hypothesis, but in this case of particularly of these composite hypotheses, one typically, often talks in terms of reserving judgment or not. So I should just mention that, I suppose. In any case, we'll call it right now accepting null hypothesis or reserving judgment unless we get 4 heads. If we get 4 heads, then we're going to declare that the coin is unfair and the world is against us. If 4 heads, then we decide on accepting the alternative hypothesis that the coin is unfair. All right, now in this situation, the alpha level, the probability of a type 1 error, is a 16th. Okay, and because a type 1 in the case of a type 1 error, we have asserted that the probability is 1/2, and therefore we can compute that. On the other hand, the probability of a type 2 error is not well defined. But of course it is. So why is it undefined? Because it depends on this parameter theta, and we haven't specified theta in the alternative hypothesis. We've just said that it's in some range bigger than 1/2. Okay, but rather than simply give up and say that it's undefined, what we're going to do today is just describe what it possibly does as a function of theta, where theta takes its values between 1/2 and 1. So what we then typically do is we define pi of theta is like the power of the test at theta. This is 1 minus the probability of a type 2 error, under theta such that we're in the alternative hypothesis, i.e., this is the probability of correctly asserting, let's say the probability of asserting H1 if H1 is true. Okay, and so what is that? Well, in other words, it's the probability of getting 4 heads, assuming that the coin is unfair, that it's in this range of 1/2 to 1, and that is, of course, theta to the 4th. Okay, so no, of course, this is really just for thetas in this range that we're considering. So, so what's the idea? Of course, you can like plot this. So it looks something like this. We're just plotting from 1/2 to 1. It has the value 1 over 1, right? This is just theta to the 4th versus theta is what I'm drawing here. And at 1/2 it has the value of 1/16. I don't know, it's like kind of flat and it like zips up like that or something like that. Something like that. Okay. So it has kind of this shape. And so what do we see? We see that that as the theta is closer to 1, the test is kind of more powerful. It correctly finds out that the coin is biased more easily in this region, and over here it's very unlikely to do so. It's not so powerful. It's typical actually to fill in this graph for all values. I guess like this is those little circle there. All possible values of theta that we're considering under both hypotheses are just in this case between 1/2 and 1, but typically one fills in pi of theta really as the probability of asserting that this is true under given theta, given our particular value of theta. And in this case, for our particular function, at theta equals 1/2, this would be the probability of asserting the null hypothesis is false under that, and that's also 1/16, so it just fills in right there. So more generally, what we would like to do is we would like to, for the test to be powerful, we want to assert that the alternative hypothesis is true as much as we can, unless that makes our type 1 errors go above alpha, right? So the basic game is make pi of theta large while having pi of theta no more than alpha for theta satisfying the null hypothesis. So we want to have a probability less than or equal to alpha of rejecting the null hypothesis in the case that we are in a situation where the null hypothesis could be true. But okay, so now the dream would be the following. So we say that we have a critical region, or really a test therefore, of size alpha is a uniformly most powerful region if of size alpha. I guess I should say of size less than or equal to alpha, because maybe I have something discrete and I have to make myself strictly less or something. But it's most powerful region of size alpha if pi of theta, if this power is strictly, not strictly, but is at least as large at every value is greater than or equal to the power function for any other critical region of size at most alpha. All right, so we would like to be able to say that we find a test such that the probability of asserting the alternative hypothesis when it's true is as large as possible, given the fact that we are mitigating our chance of a type 1 error of unnecessarily rejecting the null hypothesis of at most alpha. Okay, so it's wonderful. If we can do this, that's great. We've found a test that is like more powerful than any other test and has, and all that. The problem is, you typically can't do this. Okay, so let's just look at so this is a somewhat perverse example, but it maybe still gives some of the flavor of what's going on here. So so let's suppose we choose the very large alpha level of 1/4, just because I'm going to do this by hand off the top of my head. And again, we're going to look at a coin flip. This is going to be also due to the funniness of discreteness in this particular example, but whatever. So we're going to do 4 flips, and we're trying to determine again between these two hypotheses, right? We have H0 is that the coin is fair, and H1 is that the probability is strictly bigger than a half. So let's consider these two tests. So test 1 is that if exactly 3 heads, then we say the coin is unfair, else we reserve judgment or go to the null hypothesis. Test 2, if exactly 4 heads, then we conclude H1, otherwise we go to the null hypothesis. Now, why 3 or 4? I mean, why not 3 and 4, for example, right? Well, so now notice the probability of a type 1 error in test 1 is the probability of getting 3 heads with a fair coin, and what is that? That's so there's a binomial variable, so there's 4 flips, so there's 4 places that funny toss could be, 4 times 1/2 to the 4th, so this is 4/16, which is a 4th. The probability of if I said 3 or 4 heads, then that would increase my probability of getting a type 1 error above 1/4, which would make that test not have the right alpha level. Of course, I can look at the type 1 in test number 2, and I find that, as before, it's 1/16, which is certainly below that alpha level. So, so these are a couple of valid tests, but kind of the more obvious test of 3 or 4 heads is not allowed by our constraint of alpha being a 4th. All right. So, so these are the tests that we are going to choose from, and we can ask what are the different powers of these tests. So let's say power 1, power of test number 1. This is going to be the probability of correctly choosing the alternative hypothesis when it's true, and that is let's see. So this is the probability of 3 heads given our particular value of theta. So that is well, let's see. So there's 4 places that the tail could go. And then I have 3 heads and a tail. So that's the function for that. the probability of 4 heads for a given value of theta is theta to the 4th, and that's the power of test number 2. And so I could say, like, which test is more powerful? A very natural question. And what we find is that it depends. So if we were to draw this out, which I've done previously, we get a picture that looks something like this. So so maybe here's 1, and maybe I'll make 1. So for type 2 errors, in this case, the theta to the 4th has a graph that looks kind of like, like this, like I drew before. And this one will be 4 theta cubed 1 minus theta. And that starts out bigger. And kind of comes down. And they cross, I didn't actually calculate it, but around 0.8-ish or so. Like 4/5 or something. So it's not really drawn very well to scale, probably, but whatever. Okay. So but so what do we see from this plot? We see that for theta in this interval of roughly 1/2 to 4/5 ish, the test 1 is more powerful, right? So if the coin is closer to fair but still a bit unfair, then we're more likely to conclude that it's unfair for those values of the parameter. And for theta kind of in the very unfair range, you typically get 4 heads instead of 3 heads. If it's very unfair and tends to give a lot of heads, you'll tend to get more heads, and test 2 will be more powerful. The red stuff is above, and the chance of detecting it under test number 1 falls precipitously, because you're just it's very hard to get to get 4 heads if your coin is closer to is not super unfair. Okay. And yeah, so what do we find? We find that there's not like an obviously most powerful test going on here. Depending on the values of the parameter, one test is more, one test is less powerful. So that kind of begs the question then of what do we do? Like, how do we then find a reasonable test and decide between these different kinds of alternatives? So we'll talk about that a little bit next.